Okay, let's go and get started for today. Today I'm going to give you a new lab. You're going to have some lab time, but let's talk about the content we're going to cover today first. And that is improving performance of I/O-bound processes. And obviously this is a concurrency class. This is a topic that's related to concurrency, using a concurrent solution to improve performance of some particular application or system. Now, we previously discussed some benefits of concurrent solutions as being improved resource utilization. And that what resource utilization means is that could be something like resources within a computer. Specifically could be like the CPU as a resource. It could be some sort of other hardware as a resource. But also it could be something in the real world, like tools on a work site, making sure that they're not lying around unused and you have to buy more tools than you need. It could also be workers in a work environment. How do you make sure that you're making the most out of the workers in your workforce and not having workers sitting around waiting for other workers and getting paid and essentially slowing the job down or getting the job done. Now that brings us to the second part of that, and that's improved performance of that system. And improved performance usually is measured in how long does it take this system to complete some task. Can we do that faster? What's a faster or better way to complete that task? And one thing is that concurrent solutions can even improve performance when you don't have more than one processor. So the idea that, well, to have concurrency, you need to have a multi-core CPU, or you need to have some sort of network or cluster or cloud-based system, is simply not true. Even if you have a single CPU, a single worker, it still can be of tremendous benefit to have a concurrent solution to something. So sometimes, however, having a concurrent solution can actually hurt your performance. And there are cases where having more threads or processes or workers trying to solve something together, you can actually have it slow things down rather than make it faster. So the question becomes, how do we know what kinds of problems would benefit from a concurrent solution? And how do we know what kinds of problems might be hurt by a concurrent solution or made worse by a concurrent solution? And maybe which ones would it be not worth our time, though, because it wouldn't have any effect on it? And we already looked at some of that in the past with the what percentage can be parallelized, what percentage is sequential, how do you compute the speed up. But today we're going to talk about a slightly different aspect of that, and that is the difference between certain classes of problems. And so consider, as a thought experiment, let's consider a couple of tasks that aren't technology related. So think about preparing a meal versus the task of writing a term paper. And both of those tasks, making a meal, will have multiple steps and multiple tasks that need to be completed. Same thing with writing a term paper. But if you think about preparing a meal, there might be multiple subtasks involved in that would look like, oh, you have to cook the entree or the chicken and the vegetables, and you have to cook rice maybe, and you have to make dessert, and you have to set the table, and you have to plate the food, and then there's some things that are missing there you have to clean up afterwards. But there are a lot of these like sub-steps. Now, the idea here is when you cook something like that, like a large meal, like, I don't know, Thanksgiving dinner, or I guess we're coming up towards spring, so like Easter brunch or whatever, there might be a lot of different things that need to get done in order to have that meal ready. Now, could switching between tasks or using some other concurrent solution be beneficial for preparing a meal, or is it best done sequentially? And the obvious answer to that is that, yeah, clearly a sequential solution would take much longer. So in other words, okay, I have to bake the chicken. I don't know, it takes an hour and a half in the oven at 375 or whatever. Well, I don't know what it takes to cook the size chicken you have. But you basically would put it in there, and you'd sit there and you just stare at the oven and you wait for like an hour and a half. And then when that's done, it goes ding. Yeah, well, the chicken's done. Now I'm going to get started on the vegetables. And you sit there and you cook the vegetables and you wait for those to be done. And then once those are done, you start the rice and you wait. And once that's done, you say, oh, I got to make the dessert. So you get out the mixing bowl and I don't know, whatever kind of dessert you make a pie or whatever, and you bake it, you wait for it. And when it's done, and then you set the table and then you put the food on the plate. And at that time, everything is cold, except for maybe the dessert if it was a warm pie. So notice that how inefficient that would be, that we're spending all this time waiting. And you notice that's not really how people do that. The idea is, even if you have one person in the kitchen, you can make that much faster. You could say, okay, the chicken's going to take the longest, I'll get that started. While that's going, I'll get started on the dessert because it's got to get baked and then cool down enough to eat, or maybe it's a pie you put in the freezer or whatever. And then I'll wait a little bit, and while that's going on, I'll go ahead and set the table. So overlapping these things while I'm waiting for these to complete, I'll start doing other things. I can't plate the food yet. That's got to be toward the end. But then when the time comes, I'll start the rice, I'll start the vegetables, and then hopefully everything comes out about the same time where everything's warm and everything's ready. And then you plate the food and you give it to the people you're entertaining, your family or whatever. But you notice that, or another concurrent solution would be like, hey, have somebody come into the kitchen and help you. I'll do the chicken and the vegetables, you do the dessert, you set the table. We'll get one of the kids to start the rice, and then at the end we'll have everybody plate their own food, like a buffet style. Here's the plates, there's the food, get what you want. But you'll notice that the least efficient option here is to kind of do this sequentially in this particular type of problem. But now let's think about the writing a term paper. So writing a term paper, it still has several tasks that need to be completed, and like you create an outline, maybe you edit that outline, get it to be what you want, you write a draft, you edit and annotate the draft, maybe you read through it a couple times, maybe you do a rewrite of that, proofread it, edit it, make sure that everything flows how you want, maybe make some subtle changes there but not major changes, and then when you're done you submit it. Now, would switching between those tasks make sense? And in this case, notice it's a lot harder because all of this writing a term paper, most of that work is not waiting. It's all kind of mental work that you're thinking about what to write in the outline and you're writing it up. And then you're thinking about how you want to write the draft and you're writing it up. And so the difference between those two tasks, making a meal versus writing a term paper, would fall into the categories of I/O intensive or tasks that have wait periods in them, and CPU or mind intensive things like writing the term paper, where there's not really anything in here where we're waiting for anything to complete. And these things are also kind of naturally sequential as well. You can't really write the draft last. The draft has to come before you edit the draft. And that has to come before like the intermediate or final draft. And that has to come before the final proofreading. Although you can do some of these things and plan ahead and think through that, you really kind of have to follow that sequence. And it's all coming out of like mental work. It's all coming out of the mind and maybe call it creative as well. But then writing the actual stuff out. There's not a lot of overlap. Now you could do some overlap and have some additional help with, for example, proofreading. You proofread this chapter while I'm finishing, while I'm doing the final draft of the other one. Or I guess you could just have somebody write parts of it for you, or I'll give you the draft and you turn it into a final draft. You could do things like that. But for the most part, it's still CPU intensive. It's still mental work that somebody has to do on that. And so the answer to this is probably not. It's hard to work on any two of those tasks simultaneously or overlap them. And the why? Because there are no waits, and they kind of come one after the other sequentially just by their nature. So that brings us to that concept of I/O-bound processes or tasks versus CPU-bound. And to distinguish between those, an I/O-bound process would be something like the cooking of the meal. It has wait periods in there. So I/O-bound processes are those where waiting is often an integral part of the process. Like you try to take some action, and then you have to wait to get the result of that action. I put the chicken in the oven, I set it for an hour and 20 minutes, and then I got to wait before I can take the chicken and do something with it. Or I put the the pie in the refrigerator, and I've got to wait for it to set up. Maybe it's Jello or something like that. But you'll notice that an I/O bound process, and I/O stands for input output, that we're either waiting for some kind of input or waiting for something to accept that output that we had created. So wait is an integral part of that. So that happens in computer systems all the time. So for example, you go to try to download a file or even open a file, wait for a keyboard entry from the user, wait for files to load or a server to respond. There are all kinds of times they're waiting for either hardware or some kind of event to happen that's necessary to continue the process. So even like saving a file, you say, okay, save all of this data to a file. You got to wait for the hard drive to spin to the index and spin to the location where the file is going to go. It needs to make the right things in the file allocation table or the file system. And then you have to wait while that data gets written out to that drive. And then when that's done, then your program can continue on and do something else. But you'll notice that waiting is an integral part of that. Same thing with reading a file. To open a file, you got to tell the drive, this is the file I want. It has to look at the file system, find what clusters or sectors on the drive that's in, index to those, load them up from the drive as the drive spins, and then present them through the operating system to your program that asked for them. So if you say load this, and if you've played any AAA titles on a console, like a PS4 or Xbox One, or even on a PC game, you're familiar with having to wait for something to happen. You say, okay, let's play this level, and it'll like loading. And you got to watch the little bar load the entire stuff that's loading. The files that you need, the maps, the textures, the code modules for the AI, whatever else it loads up. It's got to load all that into memory so you can play that game, play that level of that game. And you may even notice that if you played a game like, I don't know, let's think about like Fallout. You go to an indoor area, you go to open the door, you got to wait while it loads up all the stuff that's inside the house. You exit the house, got to wait while it essentially deallocates that stuff and loads the stuff back for the outside world again. But so that waiting thing there is the kind of thing that can benefit from concurrent processes, as we'll see in a second. So when we have multiple I/O bound tasks that all need to be completed, like this. So here's process 1, process 2, all the way up to process N. And you know they each have their own action and their own thing they're waiting for. So if we run those tasks sequentially, we get a diagram that looks something like this. So we do process 1, we wait for it to finish, and then we start process 2, we wait for it to finish, and so forth all the way up to the last one. Start process N, wait for it to finish, and then we're finally done at the end. Now note that the wait periods there are blocking progress unnecessarily because we're really not doing anything here. We're just waiting. We're not accomplishing anything in this area here or here or here. We're just kind of stuck there doing nothing while we wait. So the question is, what if we started the action for P2 while we're waiting for P1? So in other words, you say start P1. Oh, there's a wait period. While I'm waiting, let's start P2. And that has a wait period. And then we'll start as many of them as we can. We'll have a wait period. And then whichever one gets done first, we'll get the result from that one. And so the idea here is that we could still make progress while we're waiting by starting other actions and waiting for those. And if one finishes, then we can be done with that action. And that's as long as the results of this first one aren't critical for performing the next action. If that's the case, we still need to have some sort of precedence where one process comes before the other. So for example, like back to the cooking food, we can certainly overlap cooking the vegetables, cooking the chicken, making the dessert, and waiting for all those things to complete. But we could not overlap plating the food. That has to come after the food is done. You can't plate the raw chicken and then try to cook it. You can't plate the ingredients for the dessert until the dessert is ready. And so there's still some precedence there, but the idea is that whatever we could overlap about these things, these actions, or these processes, we should do that because that makes better use of our CPU resources. It's not just sitting there doing nothing. It can make progress on other tasks. Okay, so how do we fix that? Well, we can execute those. If those are independent processes, we can execute those concurrently. And we end up with a diagram that looks more like this, that we start the actions for multiple things at the same time. In other words, put the chicken in the oven, put the vegetables on the burner, get out the mixing bowl and start getting ready to do that. And if something needs handled, like the chicken needs basted or whatever, then we could stop one of these actions, deal with that, and get it started again so that we're not just stuck here waiting for something to complete. And notice that that can dramatically shorten the execution time from start to stop because we're overlapping these different actions and allowing us to make progress while waiting is happening. Now, that being said, there is some overhead in creating these individual tasks and managing multiple tasks. So, for example, if you go back to the kitchen example, rather than just sitting there waiting and being focused on this, you have to say, well, I'm going to start another action, but you got to have some process or some mechanism to decide what am I going to do next. And you also have to have a process for keeping track of what other ones you were working on and what state they were in. So there's a little bit of overhead with that. The starting the threads, switching between the threads, joining them at the end to make sure everything is done when it needs to be. But overall, that model could dramatically shorten the execution time or the wait time for the entire system. And that's a reason for using concurrency. Now, if they were CPU-bound tasks, there aren't really any wait periods. You notice I just edited out the wait periods here. We basically have an action and then the result of that action. But this is all requires an active entity like a processor or a person to carry that. So this is back to like the term paper idea. There aren't any wait periods. So it doesn't make sense to try to switch between these in that case necessarily if we're never waiting for something. So hold on one second. Okay, we're back, so let's finish this up. So the idea with a CPU-bound tasks is that it might not make them any faster because there aren't any waiting periods that we can overlap. And by switching between them, we could actually make things harder for ourselves. So imagine that you have a number of tasks to do around your house, all of which require you to actively do them. I don't know, maybe you need to vacuum your floor, and you need to clean the shower, you need to clean your toilets. Switching between those doesn't necessarily make a lot of sense. Like you vacuum like one strip of floor, you turn off the vacuum, you run in the bathroom, scrub a square foot of shower, stop that, run in and scrub part of the toilet, go back and vacuum another square foot of floor. You're going to end up spending more time doing the overall task than if you just focus on each one after the other. Now, if that task included doing the laundry, now you have something you can overlap. You could start the laundry, vacuum the floor, move the laundry to the dryer, go back to vacuuming the floor, and so forth. But notice that those if it's a CPU-bound only tasks, a lot of times the overhead with switching between them and managing, starting those different tasks together and navigating them all and completing them all in a concurrent way might make the overall execution time longer. So generally what we see is concurrent solutions can tremendously help if we have an IO-bound process, but maybe not as much if it's a CPU-bound process. All right, so let's do a quick review of speedup. Speedup was essentially the ratio of the sequential time divided by concurrent. So if those are the same, the amount of time it takes for each one is the same, you get a speedup of 1.0. It wasn't any faster. But if the amount of time for the concurrent one was half of the sequential, then we get 1 over 2, or 1 over 0.5, which gives us 2. So we have a speed up of 2.0 if the concurrent one is twice as fast. If we got 0.5, then the concurrent version was half as fast or slower. And besides speed up, there are other reasons for using concurrent solutions. For example, system responsiveness. For example, as you're using Windows and you move your mouse, you want to see that thing move around the screen. When you click something, you want to see an action get taken. And I'm sure that everybody in here has run into problems where the system responsiveness has suffered for some reason, like you click to open some document and it doesn't open right away. And so you click again and it doesn't open. You click again and you're like, what is it doing? It's not opening. Click, 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 click. And then all of a sudden, 20 of them all show up on the screen at one time when it finally gets around to handling those requests. So things like system responsiveness, having a concurrent solution where even if you're doing something that's complicated somewhere else, having the system respond to you, especially for a human computer interface, can be important for the user experience. Also, ease of implementation. Sometimes it's easier to implement something with a concurrent solution, and also for real-time event processing, where some event happens, we need to take action based on that event. Like, for example, a vehicle system with the airbags in your car. When you're in a crash, you want the airbags to go off quickly as a real-time event before you're out of the car, rolling around, flying through the air or whatever, and landing on the pavement. So that's a case where you need to have an event happens, it has to have an immediate reaction to it, and concurrent solutions can help with that. But one thing that is important, like we said, it's important to understand what types of systems and processes are likely to benefit from a concurrent implementation. And it turns out that I/O-bound processes are good candidates for seeing speed up from a concurrent implementation. All right, so one example would be something like a game server. So if you have a game server, a number of clients connect to the game server, and they send to the game server the game actions that they're taking. It could be what keys they're pressing. It could be what selections that they're making for firing weapons or whatever. But anyway, that goes to the server. And you'll notice that each client is going to be sending different information for how they're interacting with that game. Imagine it's like a first-person shooter kind of game. But the server is going to take that, it's going to update the game world and the game state, but then it's got to send that back out to the individual clients. So we don't want one slow client to slow down the entire server. So for example, the server, it wouldn't make sense completely to say, stop and wait for client 1 to give me their input. Okay, I got their input. Send them the game state. Now stop and wait for client 2 to give me their input. Okay, I got their input. Now send them the game state. It would make more sense to divide that up into threads. It has a thread that's receiving input from client 1, so we're not ever waiting for them on the server. If their data comes in, great, we handle it and we process it. But if their data isn't ready yet, we still can handle the information from the other users. Can still send them the updated game world. And in fact, we could still send client 1 the updated game world data as well. So we could put each player, each client connection on a separate thread, and then the server could wait for player input and send out game state data to each client concurrently. And that makes a lot more sense. So we don't want one slow person connecting to our server and ruining the game for everybody else. Concurrent solution will be an example of that. And this is I/O bound because it's waiting for the network to send the data or receive the data to and from the client and to and from the server, depending on who's doing the sending and the receiving. Okay, so that brings us to Lab 5. And we're going to take a quick look at that, and then I'm going to give you time today to work on that. So in Lab 5, you're going to be writing a program that downloads a set of images from, not form, let me fix that. From NASA. And since some of those images are going to be larger, some of them are going to be smaller, but we're going to try to, we're going to have to request that, get the data from it, and then complete. So there's going to be quite a bit of network traffic that you're going to generate with this. But what you're going to do is you're going to write a sequential version of that where you say get image 1, got it. Get image 2, got it. Get image 3, got it. And so forth to get all of the images. And then we're going to write a version of that that kind of starts them all concurrently. It basically says, all right, let's start getting 1 and 2 and 3 and 4 and 5 and 6 and however many there are. And then as they complete, they complete. But the idea is to overlap the wait times between each of those. All right, so let's go ahead and take a quick look at the lab sheet for that. So let me switch over to that. Okay, so here's what the lab sheet for that Lab 5 looks like. And you'll notice that you have a week to work on this, but I gave you this file list, which basically has all of these. Now, this is missing the open square bracket there for some reason. I'm not sure why, because I copied and pasted this out of my code. But you'll notice there's a set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 images. And the reason I picked images from NASA is because they're kind of public domain available images that you should be able to write code and download without having them decide that there's something sinister about us downloading their images a bunch of times. Hopefully. I did have a thing in the past at my business where we decided to write, actually one of the employees decided to write a program that checked to see if the internet was alive by hitting a website for this awful webcomic called Jerk City. And what they did is they put that in a loop that ran basically once a minute and said, hey, if I can get to Jerk City, the webcomic, then that means the internet is up. Now, why that was their measure of whether the internet was up or not was a good question. But the problem was the people at Jerk City noticed this extraordinary amount of traffic coming from one, I guess, IP address, one particular domain. And it was requesting the comic over and over and over again. And since they pay for bandwidth, they were like, well, let's block that whole subdomain. So they blocked our entire IP address range. And I actually had to send them an email explaining what had happened and apologizing because I didn't want them to think that, hey, these people are somehow doing something sinister by doing a denial of service attack on our webcomic. And it is a pretty awful webcomic. But anyway, I don't think that'll happen with NASA. We did code like this previously. I think they're going to be okay with it. And it's our tax money that's paying for it, so should be okay. But anyway, what you're going to do is you're going to download each of these images. And notice I have this divided up into two different methods here. One is function 1. It says function 1. You're going to call that function download sequential, and you're going to pass to it the list of the files you want to download. And then that function is going to go through in a for loop and sequentially say, okay, download file 1. And then when you're done with that one, get file 2. When you're done with that one, get file 3. And then the downloaded files, I want you to store them in local files with the same names as the originals. The program itself should display how long each file took to download and should display the overall time to get all of them done. So in other words, for each file, it should say, for example, file 1 completed. Here's how long it took for file 1. File 2 completed. Here's how long it took for file 2. And it will show all that. And at the end, it'll say overall time, and it will show you what the wall clock time is for that. Now, how are you going to download those files from that? I would suggest using this library it's a standard Python library called urllib. But if you do import urllib.request, then you can do urllib.request.url-retrieve, and you can pass the HTTP and : / and then this file name concatenated on the end of that. And then you pass in the output file name, which would be in the local directory, which could also be the same name that we had up here. And what this URL retrieve does is it gets this thing off the internet and stores it in this local file. So that part is going to be pretty easy. So there's not a lot of work you have to do there. Note for that output file name, you should not include any of the URL parts of that, meaning you don't want to have image assets NASA gov / because this / is not allowed in file names. You really only probably want this part at the end. here. And as a hint for how to get that, I'd suggest using split. Split is a method that strings in Python have. And you can pass in what character you want to split upon. I would suggest splitting on that slash character. And then getting the last item in the list, which you can get index to index into a list and get the last item in that list. -1 gives me the thing at the very end of the list. All right, so that should get you started on that. What I would do if I were you is write the code to get one file first. Make sure you can do that correctly. And then after that, what you should probably do is then add it in a loop that goes through each of the files one at a time, gets all of them. Now, the next question, or next function you have to make is writing this second function called download concurrent. And what it does is it works the same way. You pass in the files to it, but what it's going to do is create a thread for each of the file downloads. So in other words, we're going to have a thread that you pass in the URL of the file you want, and it will open that URL, download the thing, and then save it in a file. And you're going to make a thread instance for every one of those. So you're going to start a thread for, say, this file, and then you're going to start a thread for that one, and you're going to start a thread for that one, and you're going to start them all at the same time, and you're going to join all of them, and then see how long it took to get all of the things. So the idea here is we still want to see the time it took for each one, but we want to see the overall time of all of them. And the idea is I want you to then calculate the speed up. Now, one thing is you can get the program to calculate the speed up for you by calling this function first, saving off the amount of time it took. Call this function second, save off the amount of time it took. And as a way to get time, there are a couple ways to do that, depending on how accurate you want it to be, but the time module has a function called time.time that will return a time value to you. And you can actually call time.time and it will give you the number of seconds passed since January 1st, 1970 GMT. And what I would suggest that you do is Google how to get times in Python. There are also some ways to get more accurate times in Python. I'll let you Google and figure that out if you want. But really, this should take long enough that you don't need a super accurate timer to do the profiling of it. You just use time.time. And then I want you to calculate the speed up and then say how much faster or slower was the concurrent version. If the concurrent version was twice the speed of the sequential, you'll get a speed up of 2. If the concurrent version was the same speed as the sequential, you get a speed up of 1.0. So that's what you're going to do for this lab. Really, it's not a lot of code. It might take, if you're new to Python, lists are super easy. Indexing is pretty easy. It's not like creating a giant linked list or something in C. It's actually easier than using the standard template library in C++. Lists are a built-in thing in the language itself for Python. And if you're confused on any of that, remember that I did post that guide, my kind of my introduction to Python for programmers. So you can look at that, and that does cover sequences and lists in there and how to index them, how to make a for loop that goes through them, and so forth. But that's going to be what you're going to need to do. So let's switch back to the presentation just for a second here. So essentially, looking at that diagram we saw before, that's what we're going to be doing. We're just going to basically retrieve the URL, and when we get it, then we're done. And we're going to start all of those downloads at once, wait for it to complete, and then when we're done, we'll print out the time. So we're going to start a timer here and start, stop the timer and stop. Each of these will have their own timer for each individual file. But that's essentially it. So that's all for today. Work on your labs, specifically Lab 5. And other than that, everybody stay safe. And like I said, this was a short lecture, so you should use the class time to work on the lab. Don't say, well, it's not due till next week, so I'm just going to not do it. And I'll wait until it's late get started on it. If you have problems, always remember you can email me or give me a call, or we can even set up a face-to-face if necessary. But if you're struggling, let me know, and I'll do what I can to help you. Zoom meeting, whatever we need. All right, that's it. It's kind of a dreary day outside anyway today, so good day to stay in and work on stuff.